So we're going to start developing strategies for finding limits. At first, we'll start with really easy strategies. Some limits are super easy to find, and then later, sometimes they're a little bit more complicated. So we'll finish up with a second lesson on those. In this case, we're going to start with some basic limits, things that are that you just need to commit to memory and get practice using. The first one here, 1, the limit as x approaches c of b equals b. Now this is meaningless unless we read the sentence above. So b and c are real numbers, and n is a positive integer, which we're going to need here. So the limit as x approaches c of b equals b. Well, what does that mean? We're really looking at a case where the function of x equals some constant value b, because remember b is just a real number. So let's say b equals 3. All right, so the function of x equals 3. Well, then the limit as x values approach, say, -2 of 3, what does that equal? Well, that would be the graph of the line y equals 3. And in this case, no matter what I plug in for b, I'm always going to get 3 out. So they're telling us in this property that regardless of what you plug in for your x value, you're always going to get b, or in this case 3, out. So that's called a constant function, and it has a constant limit value. For the second, we're looking at a case where the f of x, or the function of x, equals x. And we'll remember from Algebra 2 that that's the diagonal line where an input value for x just gives me an output value of the same thing. So y equals x in this case. So the limit then as x values approach, and I'm going to keep using -2, of x means whatever I plug in for x, I get out for y. So it equals -2 in this case, or it equals, you can see, c in this case. The third example, the limit as x approaches c of a polynomial function, that's x to the nth power. I'm going to use x squared just to make the example, but it tells us just plug the c in for the x and get out whatever we get. So in this case I want to choose, let me erase that, -2, just staying consistent. Tells me I can plug in -2 and square it, and it gives me a +4. And if I look at the graph, that makes sense. If I plug in -2 on a quadratic graph, the value I get out is a +4. So this is a process of evaluating limits by direct substitution. All I did was I took the input value for the limit, plugged it in to the function, or here, plugged it here, the input of -2, plugged it in for x, and decided what I get back out. Now, before we move on to some other types of limits to evaluate, let's look first at a theorem that tells us what we can do when we have combinations of functions. So in the first case, the scalar multiple value, it says that if I'm looking at a function that's really just some constant times some function of x, that I can just take the constant outside, right? I can pull the constant outside, find the limit inside, and then get my value that way, which is easier in many cases. So let's look at it. We have the limit as x values approach -2 of 3x. So notice what I've done is I've combined this first function and this second function that we did earlier into one function. Well, this is one of my favorite things to do, these properties, because I call them the take apart properties. Because you can take apart a function and treat it as a bunch of little functions, which is often so much easier. So I'm going to take this 3 and this x apart because I'm allowed to. This tells me I'm allowed to. the scalar. In fact, this one tells me I can just bring the 3 out front and write it as a 3. I'm not going to, just to prove the take apart for the scalar multiple, but you'll see in a moment that it's indeed true. So the limit as x values approach -2 of 3, and then I'm going to multiply that by the limit as x values approach -2 of x. So in the first case, the limit as x approaches -2 of 3, we've already discussed and shown that it equals 3 times, and now notice what I'm going to do. I'm just going to write 3 times the limit as x values approach -2 of x. So all I've done is pulled that scalar multiple. Scalar is just mean multiply by an integer or multiply by a number. Say a value. So I just pulled the scalar multiple outside and found the limit of everything that was left. Had I pulled the 3 out front, I would just be finding a limit of x. And so I know that that's 3 times, well, we know from before that the limit as x values approach -2 of x equals -2. And so in this case, -6 is the solution. And we would get that from direct substitution. I could have figured it out up here. Plug in -2, so the limit as x approaches -2 of 3 times x would equal the limit as x approaches -2 of 3 times -2, which would equal the limit as x approaches -2 of -6. And we know when we're dealing with a constant, that's our value. -6 is our answer. So we took it apart. We wouldn't have had to take this simple one apart, but using a simple one to make the point, that's where I ended up. Same thing here for sum and difference, exactly the same. If it's addition between the 3 and the x, you would just use a plus or a minus sign. Instead of a multiplication sign here, you would use plus or minus, and you would just get this solution, and find out whatever your answer is. So let's look at a product example real quick. So this would be something like the limit as x approaches -2 of x cubed, I'm going to say. Now in this case, we can see already that this limit equals -2 cubed, which is -8. So hold that in your thought. We're expecting -8, but we're going to use the property instead. So I can rewrite this as the limit as x approaches -2 of x times the limit as x approaches -2 of x squared, because x times x squared equals x cubed, and I chose these two because I started here. So let's look. We know that the first part equals -2, and we know that the second part equals 4. And the whole thing together is -8, and that's exactly the value we expected to get. Division, being just another form of multiplication, would work exactly the same. The only admonishment is you have to make sure that if you're dealing with a polynomial or a function over a function, that you're careful that whatever the denominator ends up being, it can't be 0. So you just have to keep your eyes open and make sure that you eliminate any values that would end up that way. But I think I will do an example of the power rule. So the limit as x values approach -2 of some function of x raised to a power. So let's say the function of x is x plus 3 to the 5th power. All right, well, I know that this is a function of x raised to a power, so I could do instead, I could just calculate the limit of the function, right? That's what L is. It says that the limit of just the function equals L. So the limit of x minus 2, or x approaches -2 of the function. And then once I get that solution, I can raise that to a power of 5. So that tells me that I'm dealing with the limit, direct substitution, right? We're still working with direct substitution. Put a -2 in for the 3. So inside the parenthesis, I'm looking for the limit as x approaches -2 of 1, but a constant function is just whatever the constant is. So that would be 1, which still needs to be raised to the 5th power. And 1 to the 5th power equals 1. So let's look now at a bunch of examples that work by direct substitution. We have a polynomial and a rational function. Again, if p is a polynomial function and c is a real number, then the limit as one approaches c on the x-axis of that polynomial is direct substitution, just plug it in. Same thing for a rational, where you have a polynomial over a polynomial. The only thing we have to be super careful of is making sure that when we get our solution that we don't have 0 in the denominator. The next example of direct substitution is involving a radical, and we have a caution here, which is that if we're dealing with a positive value for n, that we only have c values that are positive. We can't take the square root of a negative number, at least at this point in this calculus. Next, the limits of trigonometric functions. Again, these can seem tricky, but they're really just direct substitution. The limit as x approaches c of the sine of x equals the sine of c. You just plug straight in. And you might ask, why is that true that we can just plug numbers in after we've just spent a little bit of time talking about when limits are one-sided or not defined at some value of c? And the reason is all three of these functions are continuous everywhere. Now, in Algebra 2, we actually talked about that a little bit, but we didn't make it as clear as we need to now because it was sort of a non-issue. All of the polynomials, all of the rational numbers that we graphed, all of the trigonometric functions, and all of the radicals that we graphed were continuous everywhere except for wherever this caution was listed. So we have our parent functions, right? A line is continuous, a quadratic, a cubic, a root function is continuous as long as we don't choose x values that are negative. A rational function is continuous as long as we don't choose x equals 0 in the denominator. All of these, oh, and even our trig function. So sine was continuous and would go in the opposite direction, and the same thing for cosine. They were all continuous, and because they're all continuous, we don't have any danger of choosing an x input value that's someplace undefined. So we can just plug in, use direct substitution, and find out what the limit would be at that point. So let's do an example of a radical. The limit as x values approach -2 of the square root of 3 minus x. So we're dealing with a radical here, and I'm assuming I can use direct substitution. We'll find out. So the limit, this equals the limit as x approaches -2 of, I'm going to do a substitution so I don't have to write the limit part again. This equals whatever the square root of 3 minus -2 is. And I can see that I'm safe from my restrictions on the domain, so I have, that's just the square root of 3 plus 2, which is 5, and that's as simple as I can go. So by direct substitution I can find what is the limit of this function at x equals -2. One more, the limit as x values approach -2 of a rational. X squared plus 3x plus 6 over x minus 4. So first thing I want to do is make sure that I'm not going to end up with a 0 in the denominator. -2 take away 4 equals -8. I'm good to go. So that means I have cleared my caution, so now I can just plug -2 straight in. So I have -2 squared plus 3 times -2 plus 6, which is 4 minus 6 plus 6 over -8, which is -1/2. So now let's look at the limit of a composite function. And this one's kind of interesting. We've already done one, but it's kind of interesting when you look at it, that what it's telling us is that if we have f and g are two functions, so that the limit of the limit as x approaches c of g of x equals some limit L, And the same thing for f of x equals f of L. What? Let's go back here and look. That's kind of crazy, isn't it? But watch what this is actually saying. It's saying that if you have a limit of a composite function, you can find the limit of the inside function and you're done having to calculate the limit. The outside function then can just be taken. And we did that already right here, right? So let's write this down again. The limit as x approaches -2 of the square root of 3 minus x. And since we know we're good to go, we've already done all of our cautions and everything, let's see what happens here. This tells us that we can take the square root, right? That's the outside function. In this case, we would be looking at f of x equals the square root of x, and g of x, the plug-in function, equals 3 minus x. So we're going to look at the square root of the limit as x approaches -2 of 3 minus x. Well, that's just a direct substitution. 3 take away -x is a 5, positive 5, so we want the square root of 5. And look where we are. I'm in exactly the same place I ended up over here. Obviously, this was an easier way to do it up here, but knowing this about compositions of functions or composite functions helps us down the line as functions get more and more difficult. And last but not least, we start to get into some territory that we've covered already. We start looking at what happens to functions that agree at all but one point. And this would be an example of a rational function that the denominator equals 0. Such as, let f of x equal x cubed minus 1 over x minus 1. So we're good to go, except we can already tell that x cannot be 1, because that would give me a 0 in the denominator. So I already have a clear idea that I'm not allowed to look at 1, that this function exists everywhere except at inputs of 1. So let's try to define a limit at 1. Let's see if we can at least define the limit, or see if the bug walk has the bug walking from the left to a certain point and from the right to the exact same point. So I'm going to look at the limit as x values approach 1 of x cubed minus 1 over x minus 1. Well, the first thing I want to do is factor it. So the limit as x approaches 1 of, well, x cubed factored is, remember, you keep the same thing as though you didn't have the power, x minus 1, and you multiply that times the first one squared, the last one squared and positive, and the middle value is just opposite sign of a times b. So in this case, a is 1, b is -1, a times b is -1, the opposite of that is plus 1 times x, or I guess I could have called a 1x, over x minus 1. In this case, I'm able to resolve the problem by canceling the numerator with the denominator, and now I have a new function. I can call this function f of x, and I can call this function g of x, and that's what we're talking about here in our theorem 1.7, that if we can find a value that g of x equals f of x for all x in C, so excuse me, for all x that are not the constant of 1, right, in this case C is 1, in an open interval containing C, so an open interval meaning no endpoints, right, so on the interval -infinity to infinity would be considered an open interval containing 1, and 1 is definitely contained in that open interval. If the limit of g of x as x approaches C exists, then the limit of f of x exists, and they equal each other. So I can say that the limit of f of x equals the limit of g of x, in this case because we know it does because of factoring. So I can evaluate the limit of g of x to find the limit of f of x. So the limit of g of x equals direct substitution, 1 squared plus 1 plus 1 equals 3. And so I can actually say that the limit of f of x equals 3 because the limit of g of x equals 3. I can't say the function equals 3 because we know that the function doesn't exist at 1. But I can say the limit, and on a picture what that looks like is at input value of x equals 1, 3 would be a whole. So the limit is approaching 3. The limit is approaching 3, excuse me, the right-hand limit is approaching 3, the left-hand limit is approaching 3. There's a whole, so the function is not defined, but the limit is totally defined. So this method for finding a limit is called the dividing out method. So this is the dividing. Because we just divided out the problematic denominator. One more method to cover, and that's whenever we deal with radical functions that are problematic. So let's look at an example of a radical method. Well, actually, it's a radical function, and we're going to use a method called rationalizing. So you should recognize rationalizing as a term we used in Algebra 2, and indeed we're going to do exactly the same thing. So let's go ahead and give that a go. So let's find the limit as x values approach 0 of x plus 1, the square root of x plus 1 minus 1 over x. And we can see already, regardless of what happens in the numerator, the denominator is going to lead us to the problem of the limit as x approaches 0 of x. And this is where we started our whole lesson, right? This means I just plug in 0 for x and I get 0, which is a perfectly fine number except when it's in a denominator. So this isn't going to work. So we're going to use the technique we used to use for rationalizing a denominator, only in this case we're going to rationalize the numerator in order to change our function to hopefully find a limit. So I want to multiply by an expression of 1 by using x plus 1 plus 1. So this is called the conjugate, right? It's the multiplicative conjugate, and you can see quickly by looking that when we multiply these, it's like a mother's face problem, and so we're going to eliminate a radical. And then in the denominator I have to multiply by the same thing. So that would be the limit as x values approach 0 of square the first terms. I just get x plus 1 back because the square root squared, and then minus square the second terms would be minus 1 over x times the multiplicative conjugate x plus 1 plus 1. Well, in the numerator, and I'm going to write it all the way out, in the numerator I lose the 1's and I'm left with just an x. In the denominator I have that x factor times the rest. My x's cancel, and now I no longer have a problem with my denominator. I haven't defined the function at 0, but I can talk about the limit from the right and the left to see what happens. And so now I can use direct substitution, so I get 1 over the square root of 0 plus 1 plus 1, which equals 1 over the square root of 1 is 1 plus 1 is 2. And so I now have a value for my function at that undefined or problematic region. And if I were to graph this, what I would find is at 0, or from the right-hand side approaching 0, I have a function that looks to be headed to the number 2. Then I have a whole, and then I have a function that looks to be headed off to the number, well, wherever it ends up. And remember, for a radical function, you have negative values or negative radicals to worry about. And so you can see in this case on the graph, after this part I'm dealing with negatives under the radical, so the function doesn't exist over there. But I only cared about what was happening at 0.